Okay, just going to go through the question you were asking me about yesterday, which is the method of mixtures question. And the question, if you remember, it was question 3, is about water, 2 kilos of water, 15 degrees Celsius, and it's minding its own business, but then somebody comes and puts a 0.8 kilogram block of copper into it, which is at 76 degrees Celsius. And the question was asking you, what is the final temperature of the copper and the water? So this is a method of mixtures question. You can tell because you're putting something into something else. So sometimes you get questions where you might have hot water being put into cold, or steam being put into coffee. Anything where you've got something going in something else, the principle comes down to the same, that the heat lost by one thing, in this case it's the copper because it's cooling down, is equal to the heat gained by something else, which in this case is the water, because it will end up warming up. So that's a starting point, and just write that down so that you know what you're doing. And obviously to calculate heat, in this case, we're going to be using specific heat capacity because there's no change in state involved. So start with the copper. The energy lost by the copper is going to be mass times the specific heat capacity of copper times the temperature change. Now the copper is going to go from 76 degrees Celsius down to something else. So the change in temperature is going to be 76 minus whatever the water copper ends up at. So I'm going to call that X. Okay, so that's X is the mystery new temperature, which is the purpose of the question. Now the heat gained by the water is going to be the mass of the water in this case, times by the specific heat capacity of water times the change in temperature. And in this case, it's going to be warming up. So it's going to be the final temperature, X minus 15, which is what it was to start off with. Okay. So now what we have to do is just substitute some numbers in and multiply out the brackets. So the mass of the copper is 0.8 times the heat capacity of copper, which we're told is 400. Times 76 minus X is equal to the mass of the water, 2 times the heat capacity of water, 4,200, times by X minus 15. Okay, so again, it's just a case of multiplying it out and multiplying out the brackets. So 0.8 times by 400 is 320. 320, 76 minus X is equal to 8,400, X minus 15. Now, again, everything inside the brackets gets multiplied by everything outside the brackets. So 320 multiplied by 76 is 24320, and it's going to be minus 320x is going to be 8,400x minus 15 times 8,400, which is 126,000. So we're just going to gather the x's on one side of the equals sign. So that's going to give me 24320 plus 126,000 is 8,400x plus 320x. So 150,320 is equal to 8,720x. So x is going to be equal to 150,320 divided by 8,720. X is 17 degrees Celsius, which kind of seems like a reasonable finishing temperature. So after the copper's finished cooling down and the water's risen up, the equilibrium point will happen at 17 degrees.